Good morning, friends. I am in the process of delivering my lectures for flight mechanics. This flight mechanics is in 4th semester of Aeronautical Engineering students in Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have completed my 8 lectures. In these 8 lectures, I have discussed about atmosphere, I have discussed about the lift, I have discussed about the drag, I have discussed about the drag polar, I have discussed about the relation between the coefficient of lift and the wing loading. In the previous lecture, I have discussed about equations of motion and thrust required. In today's lecture, I am going to discuss about power required. So, power required and excess power. These are the two topics which I am going to cover. And you have seen that in the previous lecture, if the aircraft is flying in this way, there is a drag. This drag will try to pull back. That is the drag which is that much force we need to pull the aircraft. That is called the thrust required. We have also discussed that engine is producing some thrust. That is called the thrust available. Always thrust available should be more than the thrust required. Then only aircraft will be able to fly. If it is thrust required and the thrust available both are the equal, aircraft cannot climb. Only that it will maintain the same speed. There is a difference between the power required and the thrust required. For the propeller engine, we use the power required, and for the jet engine, we use the terms thrust required. So, I am going to discuss about the power required and the excess power in today's lecture. I am Dr. Dwivedi, professor from Institute of Aeronautical Engineering, Hyderabad, India. In today's lecture, I am going to take some topics. Those topics are discussed, written in this overview. Power for the jet engine. Thrust required for unaccelerated flight. Procedure to find thrust required. Power required and available. Velocity for a minimum power and the minimum thrust. CL required for power required minimum. These are very basic concept of any flight mechanics or aircraft performance. We as an aeronautical engineer must understand this concept. Otherwise, aeronautical engineer without flight mechanics or stability and control, you are not the engineers of aeronautics. Other than this topic, if you see the aerodynamics, structures, propulsion, some other branch of engineering is working on that. But if you see in flight mechanics and aircraft stability and control, only aerospace and aeronautical students are working. So it is very core domain for each and every aeronautical student where you can distinguish yourself that you are the aeronautical engineer. If you see the aerodynamics, your mechanical, biological, chemical, all these engineering students are going. If you see the structure, civil engineering, mechanical engineering, they are also going. If you go for the propulsion, your mechanical students are also working on that more than the aeronautical. So, this is only the domain where aeronautical engineer has to excel better than anybody else. In this domain, only aeronautical people are employed and aeronauticals are working for the design and development of the flight controls, flight systems and all. So, in my previous lecture, I have discussed about equation of motion. We have derived that L is equal to weight, lift is equal to weight, and thrust is equal to drag. And we have seen the formulation, how to find out. We have also find out the thrust required, and we have also done this plot TR versus velocity. This thing we have, this is the parasite drag, This is the induced drag. This is the total drag. This is the TR. This is the velocity. Okay, so this we have already done in our last class. Just I will discuss about the Man Ki Baat. In Man Ki Baat, you know that our Prime Minister of India, Honorable Modi ji, is every month he is telling about Man Ki Baat. Here I also thought that I will also do about Man Ki Baat for aircraft performance or the flight mechanics. If you see the aircraft, how the aircraft is moving, how we can control the aircraft. If you want to make nose up, if you want to make nose down, if you want to roll the aircraft like this is the rolling. If you want to roll the aircraft, you want to pitch the aircraft, you want to yaw the aircraft, how you can do it. And if you are doing like this, what are the forces which are disturbed? How the atmosphere is working to make the... Okay, this is the aircraft. And here is the wing, here is the tail, here is the rudder, here is elevator, this is the aileron, this is the, just I will put here, elevator, and this is the rudder. These are the some basic component of, and this is the wing. This is called fuselage. This is the canopy. Here is the cockpit. Here is the center of gravity, CG. These are the some important component. But how we can say that aircraft is in cruise? And we have seen the phases of the flight. This is called the phases of the flight. This is the ground run. This is the climb. This is the cruise. This is the descent. This is the loiter. This is the landing. This is the cruise. This is the climb. This is the descent. This is the loiter. Okay, so these are the phases of the flight. So if you want, on the ground, engine is started. After the starting, it will wait on the runway. After clearance from the ATC, aircraft will start running on the runway as and when the speed of the aircraft, as and when, this is the runway, as and when the speed of the, it is V is equal to 0, and when it is reached a certain speed, V take off, then it will start nose up, rolling up to, then it is like this, and then it will start climbing. So till the time 15-meter height, this is the height, it means your takeoff is completed. So from here to here, this is the ground distance for the takeoff. If the aircraft is running, it is 15 meters from the ground, it has crossed, then aircraft is takeoff, not up to here only. So this much runway is required. On top of the runway only, the aircraft has to reach 15-meter height. And this how we are achieving? By the help of the engine thrust. Engine thrust is pulling. As and when it is takeoff velocity is reached, it will be nose up like this, and it will start climbing like this. So there are some forces, there are some moments, those are involved. In the previous class, we have discussed about equations of motion. Equations of motion, lift is equal to weight, thrust is equal to drag. But for takeoff, how much lift is required? So this half rho v square s cl. So CL is equal to 2 W by S divided by half this rho V square S. That much CL is required. If you know the weight and the area and these all things, so how much velocity is required, that we can find out by help of this equation. So these things are very much used. So now I will go for the power for the jet engine. A jet engine derives this thrust from compressing incoming air and then mix it with fuel to burn it and then exhausted the hot gases at high velocities through a nozzle. The power available from a jet engine is given by the equation PA is equal to TA into V, where TA is equal to thrust required, which we have discussed, thrust available, and V is a velocity of aircraft. So power available is equal to thrust available into velocity of the aircraft. And if you see here, this is the jet aircraft, turbojet, and here thrust available is mostly constant. It is not 100%, but if you see the velocity here in this thing, it can go up to this velocity. But if you see the propeller, this thing, it is going like this. So at a certain velocity, a sharp decrease of power is there. So it can be seen from the figure that the thrust from a jet engine remains reasonably constant with respect to the velocity. So it is not matter about the velocity. Mostly it is only 2-3% changes may be there, but mostly it will remain the constant. Now level unaccelerated flight. We have already derived these equations of motion. T is equal to D, L is equal to W, and we have seen that TR is equal to, that is the thrust required. Thrust required. TR is equal to W by CL by CD, or we can write W by L by D. So when thrust required, we need minimum. It is like a drag. So if we need the minimum thrust required, then CL by CD should be maximum, or this thing should be maximum. So to have the thrust required minimum, we need the CL by CD maximum. So the object of V engineer is to make your design in such a way that the L by D ratio or the CL by CD ratio of the aircraft should be maximum. So here we can see here T is equal to D, it is half rho V square S CD. L is equal to W, half rho V square S CL. So if we make T by W here, so these things will be cut here, and here you will get CL by CD. So T by W is equal to CL by CD, or T is equal to W by CL by CD. So this you can see from here. So here the thrust required, TR is the thrust required to fly at a given velocity in level and unaccelerated flight. As of now, we are only discussing that dV by dt is equal to 0, and the rho is constant, m is constant. Okay, rate of change of mass also constant. These all things are constant. Notice that the minimum TR is when this TR is minimum when airplane is maximum L by D. So that's why I told you that we have to design in such a way that either lift should be more or drag should be less, or the L by D should be high. This is our objective for any designer, to make sure that your aircraft is meeting L by D is maximum. L by D is an important aero performance quantity. Now we will discuss about thrust versus power. Okay, so how this thrust and power are related with each other. Thrust is a force with the units Newton, that is kg meter per second square. Meter per second square is a acceleration, so it is a MA. For example, the PW 4000-112 is rated as in 98,000 pound of thrust. So it is like Newton, it is a force. Piston driven engines are usually rated in terms of power. Power is a precise term and can be expressed as energy per unit time. Energy per unit time is a power, or rate of change of energy, rate of change of doing work is a power, and this unit is kg per meter square per second or kg meter square per second, kg meter square second cube. We can write this as a watt. So note that energy is expressed in joule. The joule is what? It is a kg meter square per second square. And if you make one more second, it becomes the watt. Force into velocity with the units kg meter per second square into velocity meter per second square. It has become kg meter square per second cube. Usually rated in terms of horsepower, and 1 horsepower is equal to 550 feet pound per second or 746 watt. Example is airplane is level unaccelerated flight at a given altitude with speed of V infinity. Now thrust requirement. This we have already discussed in detail about this in the previous lecture, but we will give some glimpse of this thrust required. TR for airplane at a given altitude varies with the velocity. So this TR is directly related with the velocity. Thrust required curve, TR versus, it is given here that it is in pounds, 200, 400, 600, 800 and 1000. Here the 100, 200, 300 and 400, and this is the L by D maximum. At the L by D maximum, you will get TR minimum. So this is the objective of this plot, to find this thing. Then how to find the thrust required? What is the procedure to find the thrust required? That I am going to discuss here. This is the same plot which I have shown earlier. Minimum TR when airplane flying at L by D maximum. So this is the L by D maximum, and if you draw a horizontal line, this is the TR minimum. So how to find it? Select a flight speed, that is V infinity. Calculate the CL, and how to calculate? It is equal to lift is equal to weight. So CL is equal to W by half rho infinity V infinity square, where rho infinity and V infinity is the density at the atmosphere and the free stream velocity of the atmospheric air. Then we have to calculate the CD, because we know that thrust required is equal to W by CL by CD. So we can find out CL here and CD from here. And we know that this is the drag polar. CD is equal to CD naught plus CL square by pi E aspect ratio. From here we can find out the drag. Now you divide CL by CD. Then you know the weight. So TR is equal to weight by CL by CD. So you can see the method to find out the thrust requirement. This is how much thrust engine must produce to fly at selected V. So at this velocity, how much thrust required you can find out by using these equations. So thrust required is equal to W by CL by CD. So this is the point which indicating the maximum L by D, where you have the minimum TR required. Now, thrust requirement. Different points on TR curve corresponds to different angles of attack. You know that L is equal to W from the equations of motion. So L is equal to W, T is equal to drag. So half rho V square, half rho infinity V infinity square SCL is equal to, we can write Q infinity SCL. This is the dynamic pressure, Q. Q SCL, and we know that D is equal to Q infinity S CD, Q infinity S CD naught plus KCL square here. And if you see here that TR versus drag. So here we have the 2 points A and B. So increasing angle of, as you reach to less speed, this is the less speed. Less speed, you need to increase the angle of attack. Angle of attack has to be increased. So if you are going from here to here, as you reach at the stall, this is the highest angle of attack. Highest angle of attack, then your stall will happen. This is the stall speed. This is the max speed. A max speed, if it is, this is the max speed. In this way, you can get the speed. So, what will happen at the point A? In this point, what will happen? Large dynamic pressure, a small CL, and a large drag. A high drag is there. But as you go here, at here, you will have the minimum drag here. But here also again, drag is also increased. At B, small dynamic pressure, large CL or CL square, and alpha to support weight and large drag. So these are the scenarios at the point A and at the point B, which are very much essential to understand that at which speed you have to fly. You cannot go beyond this. You have to fly in between. Always try to fly here or here somewhere. It is always good to fly in this condition. So thrust required versus the flight velocity. So TR is equal to drag Q infinity S CD. TR is equal to Q infinity S CD naught plus Q infinity S CL square by pi E aspect ratio. This is called the zero lift drag. This is called the lift induced drag or TR. And if you see this plot here, this is the zero lift drag. This plot is zero lift drag, and this is the lift induced drag, and this is the total drag. And this is called the total TR. So this point is very important, where you have the V L by D maximum. Where you are flying at L by D maximum, that velocity is called the TR minimum. How fast can you fly? This is what velocity we have to fly. So that is very important. So maximum flight speed occur when thrust available TA is equal to TR. That is the ultimate point where your engine power and the drag is equal. Reduced throttle setting. So if you are in that position, your TR should be always less than TA. Cannot physically achieve more than TA, which engine can provide. So you cannot increase that. So you can see here that if I am drawing a plot, TR versus the velocity, and here is the TA. So this is the point, and this is the velocity. As per this, it is nearly 975 feet per second. This aircraft can fly up to here only. So if you see here, TA is a partial, and here TA is full. Means full throttle is given. Like your bike, if you are giving full accelerator, it is going. So how much full you can give? It cannot go 200. So As per the design of this thing, if you give the full throttle, it may give 80, 90, 100 kilometers per hour. But after full throttle, it cannot go beyond. That is why this is the point where, full throttle, and this is the velocity maximum with full throttle. Okay, so these are the two things which we have to very much, how much fast we can fly. You cannot fly faster than this. Here you cannot fly. Here. This is not possible because TA not available. Not available. Maximum up to here only. You can fly here, here. But you cannot fly beyond this. So that is the maximum flight, how much you can achieve. I think it is very much clear. Now I will talk about the power available. Propeller driven engine. If you see here, the power available for the propeller driven engine is falling as the speed is increasing. So this is the propeller and piston engine. Okay, that it is as per the velocity and as per the altitude also. The efficiency is decreasing like Cessna aircraft. If you see about the jet engine, as per the velocity, it is not decreasing. It will before, I think this is the Mach 1. So up to Mach 0.9, it will make the aircraft constant speed. And this is here the jet engine, turbojet engines are used. So very unique features are there. For the propeller IC engine aircraft, you cannot go very high speed. At the low speed, it will give more thrust. If you see here, low speed you have more thrust. As you increase the speed, thrust is very less. Thrust available is very less. So it cannot climb, it cannot do so many maneuvers as the jet aircraft will be able to perform. So here power available now. So if you see here, for the propeller driven engine, TA is like this. For the jet engine, TA is like this. This is for the propeller. Power available, it is as a velocity, it is like this. And for the power available for the jet engine, it is constantly, it is increasing from 0 to maximum. Here at the 0, you have this much speed is required. It will go up to here only. But it is straight, as you increase the speed, it is going to increasing. And here it is up to certain, it is increasing and then start falling down. Power required versus V infinity qualitatively resembles the same as TR. It is almost same. Power required, it is like that. So formulation of the power required, I think for IC engine propeller configuration, power required PR is equal to TR into V, and we know that TR is equal to W by CL by CD, and V is equal to 2W by S by rho CL. And if we club it, we will get here W to the power 3 by 2, CL to the power 3 by 2 by CD under root 2 by rho S. For any V, CL and the rho given, if W is known by CL by CD, we can get the power required. For a minimum power required, PR minimum, CL to the power 3 by 2 by CD should be the maximum. Now, what is that CL? In which CL 3 to the power 3 by 2 by CD is the maximum. So L is equal to W is equal to half rho V square S CL. So CL is equal to 2W by rho V square. So this is the CL at which if we fly, we will get CL by CD maximum. So power required is equal to TR into V. TR is equal to D drag into V. Drag is equal to half rho V square S CD naught plus KCL square into V. So here half rho V cube S CD naught, because this we have multiplied here, plus here we can write CL is equal to 2W by S divided by rho V square. So 2K W square by rho SV. It is called the zero lift power and it is called induced power. If I draw the plot PR versus V, so here PR versus V, this is the your induced power and this is the zero lift power. Okay, so if you see here that at this point it is shifting towards the right. So for the minimum power, CL to the power 3 by 2 by CD should be the maximum. What is that CL in which power required is minimum? So we will see by this equation, we will differentiate. So here dPr by dV is equal to 0. So 3 by 2 rho V square S CD naught plus minus 1 by 3 CL square by this. So now this all will be 0. CD naught minus 1 by 3 CL square is equal to 0. So CL is equal to under root 3 CD naught by K. So CL for the minimum thrust is under root CD naught by K, but for the minimum power it is CL is equal to 3 CD naught by K. This we have to understand that this is for the minimum power, minimum CL, and this is the thrust minimum CL. So CL for the power minimum is more than the CL for the thrust minimum. So plot for the minimum thrust and the minimum power. So if you see here that this is the plot for, if you draw, this is for the minimum V minimum thrust and this is the V minimum power. So if you draw like this, if you draw this tangent from here and wherever it is touching, this is the minimum thrust and the lowest value is for the V minimum power. So this is the difference between, and V minimum power is less than V minimum thrust. That we have to very much clear about that V minimum power is less than the V minimum thrust because the CL at the minimum power is more. CL at minimum power is more than CL of minimum thrust. So in the next lecture, I am going to discuss about excess power, power available, power required, effect of altitude, absolute ceiling, service ceiling. These are the references which I am going to undertake in this course. I have taken the references from these books: Anderson J.D. Jr., Aircraft Performance and Design, International Edition, McGraw-Hill's, first edition, 1999. SL by ME, Aircraft Performance, Theory and Practice, AIA Education Series, AIA 2. Any questions, you are welcome to ask to Dwivedi @gmail.com. I request you to like and subscribe this channel. If any queries, any comments, do comments in the comment box. Thank you very much for the joining. Be tuned for my next lecture. Very interesting. Till then, goodbye. See you.
Like, share and subscribe. Hit the bell icon for more updates.